Welcome back. Now we are moving to part B of our internal test, which focuses on similarity and dissimilarity in feedbacks. This session is all about understanding how to measure distance between the different data points, which is fundamental in data science for clustering, for recommendation system and pattern also. We will cover the four questions dealing with various distance metrics and their application also. So now let's start it. Now the question number 5 asks us to briefly outline how to compute dissimilarity between students' feedback profile for four different types of attribute. This is important because different types of data require different distance measure. Let's start with part A. Normal attributes like department or elective chosen. Nominal attribute are categorical and with no inherent order. For example, computer science and mechanical engineering department. Neither is greater than the other. The best method here is the simple matching coefficient. The formula is simple. Count the number of the mismatch and divide by the total number of attribute. For example, if student 1 is from CS department and choose data science electives, while student 2 is also a CS but choose mechanical learning electives, we have one match department and one mismatch electives, so the dissimilarity is 1 divided by 2, which equals 0.5. Alternatively, we can use one hot encoding, converting each category into binary variable and then compute the having distance. Now the part B. In the part B, asymmetric binary attributes like whether students attend workshop or not. This is tricky because not attending should be treated uh, differently because we use the jacket coefficient here. The formula is jacket coefficient is dissimilarity equal 1 minus divided by sum of a and b and c. Now let's explain what they latter mean. The a is the both students attend one and both attend one by one means and b is when the only first student attend 1 0, and the c is attend only second students attended 0 by 1. And crucially, we ignore case where both didn't attend, means 0 by 0. What so the question is, why is asymmetric? So because of two students both didn't attend the same workshop, it does not really tells us they are similarly, they might have different interests entirely. Now let's say student 1 attended AI workshop and web workshop but not ML. Now let's second student, while the second students attend AI and ML but not web, we have equal 1 for AI but B for 1 for web and C 1 for ML. The jagged dissimilarity is minus 1 divided by 3, which is equal to 0.67. So the part C, numeric attributes like CGPA and attendance percentage. For the numeric data, we use Euclidean distance, but with an important pre-processing step, normalization. Why normalize? Because CGPA range from say 5 to 10, while attendance range from 0 to 100. Without normalization, attendance would be nominate the distance calculation unfair. The normalization formula is take the value, subtract the minimum and divided by the range. Range will be max minus minimum. So after the normalization, we apply the standard including formula. So the formula is square root of the sum of squared difference. For example, if a student 1 has a CGPA 8.5 and 85% attendance, and while the student 2 has a CGPA 7.0 and attendance 70%, and after the normalization, this to a 0 to 1 scale, we would get a normalized value is of about 0.7 and 0.85 for student 1. For student 2, we get 0.4 and 0.70. The equivalent distance work out the about 0.335. Finally, the part D. And the part D, text frequency vector from keywords in open text feedback. So for the text data, we use conjoint dissimilarities, which equal 1 minus conjoint similarity. First, we convert text to frequency vector. If the student write excellent teaching good, we go get a vector excellent appear one time, teaching appear two times, good appear one time. So conjoint similarities. So measure the angle between two vectors. The formula is dot product of the vector divided by the product of the magnitude, product of their magnitude. Why use conjoint for text? So because of its capture semantic similarity regardless of document length. A student who write a long review might use the same word more times. But the conjoint similarity while still correctly identify similar sentiments. In one example, if the conjoint similarity is 0.707, dissimilarity will be 1 minus 0.707, which equals 0.293. So the question number 6, give us two student faculty interaction profile and ask us the compute four different distance measure. This is the great exercise to see how different metrics can give us the different perspective on the same data. So the profiles are given. The profile is 1 22 1 42 10, and the profile 2 20 0 36 and 8. These numbers represents are in metering, project review, attendance, assignment submitted, and infrastructure some uses count. Now let's compute part A. So the part A is Euclidean distance first. So Euclidean distance is the straight line distance in multi-dimensional square space. The formula is square root of the sum of the square difference. So we calculate. So the calculation is 22 minus 20 is 4, squared is 4, then 1 minus 0 is 1, squared is 1, then 42 minus 36 is 6 and squared is 36, and finally 10 minus 8 is 2 and squared is 4. So adding this up, 4 plus 1 plus 36, 4 equals to 45. The square root of the 45 is approximately 6.71. This is the standard geometric distance we are all familiar with. So Manhattan distance. Now the part 2b, so also called as taxi cab distance or L1 norms. Manhattan distance is the sum of the absolute difference. Think of it like traveling through city blocks. You can't cut diagonally through the building. The calculation is simpler, just adding the absolute difference without squaring. So the absolute value is 22 minus 20 is 2, absolute value of 1 minus 0 is 1, and absolute value of 42 minus 36 is 6. So the absolute value of 10 minus 8 is 2. So the sum them 2 plus 1 plus 6 plus 2 equals to 11. So notice that Manhattan distance is always greater than equal to the Euclidean distance. So it's more sensitive to difference across all dimensions. So the part C, Minkowski distance with h equal 3. The Minkowski distance is a generalization when h equal 1. We get Manhattan distance when h equal 2. We get Euclidean distance as h approaches infinite. We get the supremum distance. For h equals 3, the formula is take the sum of the absolute difference raised to the power of 3, then take the cube root. So 2 cubed is 8, 1 cubed is 1 and 6 cubed is 216 and 2 cube is 8. So sum of all the cubes, we get 233. The cube root of the 233 is approximately 6.15. So notice that it fell between this supremum and Euclidean distance, which makes sense mathematically. So part D. So in the part D, supremum distance, also called Chapsby distance. So this is the simplest conceptually. It's just the maximum absolute difference across all the dimension. So our difference are 2, 1, 6 and 2. So the maximum is 6. So the this matrix say I only care about the worst dimension. It is useful in scenario like chess where a king can move diagonally. So what matter in the maximum coordinate difference? So comparing all fours. So in the comparison of all fours, supremum 6 smallest only care about the worst dimension. Minkowski with H3 6.15 and the Euclidean 6.71 and the Manhattan is 11, largest sensitive to all dimension. So each matrix has its use depend on your application. So what aspect of similarity what matter most? Now the question number 7 discusses the median score as a holistic indicator of performance. The challenges is how to do we compute or approximate the median efficiently when dealing with massive data set, millions or even billions of records. So computing the exact median requires sorting the entire data set, which is O log n log n times complexity. That's expensive. So we a smart heuristics. So let me present five practical approach. So first approach is the sampling based approach. This simplest just randomly sample 1 to 5% of your data and compute the median of your of this sample. For a quick dashboard or real time estimate, this work great. So typically great within 2 to 5% of the true median, and it's a blazing fast. So perfect for when you need a quick answer. So the second is the histogram based method. Remember a question 3 where a calculate median from group data. Same principle. So create frequency bins, build a histogram and estimate the median using communicative frequency. The beauty is you don't need to store individual value, just bin count. So this is excellent for extreming data or when memory is limited. If your bins are fine grained enough, you are achieve 98% plus accuracy. So third is cortical scratch algorithm like T digest or Q digest. These are sophisticated data structure, specially designed for the problem. They are one pass algorithm, meaning you only need to scan your data once, and they use constant memory regardless of data set size. They provide a configurable accuracy. You decide how much error you can tolerate. So this is what big data system like Spark and Hadoop use initially. You can get 99% accuracy with very small memory footprints. So the fourth is parallel processing. Divide your dataset into chunks, process them in parallel, so maybe across multiple machines or cores. So each chunks computes its local median. Then you aggregate this using a weighted median formula. The given you exact result is implemented properly and scale horizontally with more machines. So perfect for distributed computing environment. So the fifth is incremental or online median using the two heap technique. Maintain a max heap for the low half of your data and mean heap for your upper half. So as each new data point arrive, insertion takes all login times, but the retrieving the median is instant o 1. So this is the exact and approximate. This the trade-off is you need all the data in memory, so it's the best for moderate size real time system. So balancing accuracy versus efficiency is the key decision for massive data set. Our 10 millions record are recorded using a cortical scratch algorithm or histogram method with an error bound of 1% or less. So quick estimate and dashboard sampling is perfect. For distributed system, go and parallel processing. Choose based on your specific constraints. So this all about in this question. So let's cover next question. So finally, the question number 8. This is a practical similarity analysis problem. We have feedback data from 5 students on 2 attributes: faculty responsiveness and infrastructure support. So our data is A1 for 1.5 and 2.0, and A2 1.7 to 1.9, and S3 1.6, 1.8, and S4 1.2 and 1.5, and S5 1.5 and 1.0. So now we get a new query point x equal 1.4, 1.6, and we need to rank the existing students by similarity. So part 1. So in the part 1, ask us to use multiple distance metrics that compute them all. So starting with including distance for A1. For A1, the square root of the 1.4 minus 1.5, the squared plus 1.6 minus 2.0 squared, the square root of 0.01 plus 0.16, which equal square root of 0.17, approximately 0.41. So for A2, square root of 1.4 minus 1.7 squared plus 1.6 minus 1.9 and squared, that's square root of 0.09 and plus 0.09, approximately 0.42. For S3, the square root of 1.4 minus 1.6 squared plus 1.6 minus 1.8 squared, that's square root of 0.04 plus 0.04, approximately 0.28. For S4, square root of square root of 1.4 minus 1.2 squared plus 1.6 minus 1.5 squared, that's square root of 0.04 plus 0.01, approximately 0.22. For S5, square root of 1.4 minus 1.5 squared plus 1.6 minus 1.0 squared, that's square root of 0.01 plus 0.36, approximately 0.61. So our Euclidean ranking from most to least similarity is S4, S3, and A2, A1, and S5. S4 is most similar with the distance 0.22. Now maintain distance. So in the maintain distance for A1, absolute value of 1.4 way minus 1.5 plus absolute value of 1.6 minus 2.0, and then we get 0.1 plus 0.4 equals to 0.5. For A2, 0.2 plus 0.3 plus 0.3 equals 0.6, and for S3, 0.2 plus 0.2 equals 0.4, and the S4, 0.2 plus 0.1 equals 0.3, and S5, 0.1 plus 0.6 we get 0.7. So Manhattan ranking, same order: S4, S3, A1, A2 or S5. The actual distance are different, but the ranking is consistent. So premium distance for A1 maximum of 0 0.4 and 0 0.4 equal 0 0.4. For A2 maximum of or 0 0.3 and 0 0.3 equal 0 0.2, 0 0.3. And for S3 maximum of 0 0.2 and 0 0.2 equals 0 0.2. And for S4 the maximum of 0 0.2 and 0 0.1 equals 0 0.2. And for S3 S5 maximum of over 0 0.1 and 0 0.6 equals 0 0.6. So premium ranking we have a tie. Both S3 and S4 are equally similar at 0 0.2 than A2, A1 and S5. Finally, cousin similarities. This requires a bit more calculation. We need to compute dot products and vector magnitude. For our query, x equals 1.4, 1.6. The magnitude is square root of 1.96 plus 2.56, which is 2.13. For A1 equals 1.5, 2.0. The dot product is 1.4 times, and 1.5 plus 1.6 times 2, which equals 5.3. The magnitude of A1 is 2.50. Cousin similarity is 5.3 divided by 2.13 times 2.50, which is equal to 0.996. I will spare you all the details calculation, but after the computation of all the students, A2 has the highest consistency and 0.998 most similar. S3 and S4 both have 0.997 and A1 has 0.996. S5 has the lowest at 0.965. So notice something interesting. We have constant similarity, the ranking changed. A2 is the now most similar. This is because conjoint measure the angle between vector, not their magnitude. All their profile are pointing in very similar direction, meaning they are have similar pattern even if the absolute value different. Now part B, normalize to unit length and recompute equivalent distance. So normalization means dividing each vector by the magnitude to make all vector length 1. For x, divide 1.4 and 1.6 by 2.13, so we get 0.657 and 0.751. For A1, divide 1.5 and 2.0 by 2.50 to get 0.600 and 0.800. And soon on for all vector. Now when we compute equivalent distance on the is normalization vector, distance to S3 is 0.008. To most similar distance to A2 is 0.012, and distance to S4 is 0.042, and distance to A1 is 0.063, and distance to S5 is 0.263. Here is the key insight. When you normalize vector to unit length and then compute equivalent distance, it mathematically related to conjoint similarities. In fact, the squared distance equal 2 times 1 minus conjoint similarity. So normalized equivalent distance and conjoint similarities are giving us similar information about angular difference between vectors. So now that's it why it's a text mining and recommendation system. People often use conjoint similarity. It naturally handle the normalization aspect. So at the last conclusion and the complete part B, we covered the question number 5, how to measure dissimilarities for different data types, and for question number 6 we covered 4 different distance metrics and their properties, and question number 7, efficient heuristics for medium computation in big data, and question number 8, practical similarity ranking using multiple metrics. So the key takeaway is that different distance metrics capture different aspect for similarity, and choosing the right on depend on your specific application and data characteristics. I hope this was helpful for you, and at the last, don't forget to like and subscribe, and thank you for watching this video.